This is problem 9-57 on page 479. The gravity wall is made of concrete. Determine the location, x bar, y bar, of the center of mass G for the wall. Now there are some dimensions given here. I'm going to go ahead and include a figure for the sake of the camera. I'm not going to draw the whole thing with all of its dimensions. Rather, what I'm going to do is show you how I chose to break down this composite figure into simpler bodies. So the lower body I call body 1 is sort of the base, and then I chose to take a triangle, a rectangle, and then another triangle for the various pieces. Now these two are supposed to be, this corner is supposed to be, or this vertex is supposed to be located vertically from the right edge. Now the height is 0.4 meters. And the width of the base is 3.6 meters. The height of each of these pieces, I'll put it over here, it'll fit better, is 3 meters. And I call this triangle section 2, here section 3, and over here section 4. And to note the location of the center, notice for triangles you go up a third and over a third. And that's where the centroid's at. For a rectangular piece is right in the middle, and similar again for a triangle right about there. So the location of the centroid, at least approximately, is given as I've drawn them. Now the base of this triangle is 0.6 meters, and the width, despite my drawing, of the rectangle is 0.6 meters, and then the base of this triangle too is 1.8 meters. Okay, so some dimensions just for the sake of our calculations. X is here, and Y is off of that corner. Okay? So I made a table with the various areas labeled 1, 2, 3, and 4. The centroid of each of these areas I've noted in the table. For example, x bar or x tilde for area 1 would be half of 3.6 meters, so 1.8 meters. For item 2, what would I have to do to figure that out? Well, what I would do is take 3.6, subtract 0.6, so 3, subtract 0.6 again, 2.4. That puts me right here at 2.4. And then move back a third of 1.8. Well, if we take a third of 1.8, that's what, 0.6 also? So where were we? 3.6, 3, 2.4, take off another 0.6, and we're at 1.8. So the location of the centroid of triangle 2 is at 1.8 meters. It happens that it's right above the centroid of body 1, despite the fact I didn't draw them that way. If I had drawn it more accurately, that's what we would find. For body 3, I'd go to 3.6, subtract 0.6, so at 3, subtract 0.3, and be at 3.3 meters. For the, well, but I got that wrong, didn't I? Let me try again. Area 3, yep, this one, so 3.6 less 0.6 would be 3. Yeah, 2.7. I added instead of subtracting. There we go. All right, so then, I should just work off my sheet, but I hate doing that. So then for body 4, or area 4, it'd be 3.6 meters minus 2/3 of 0.6. Okay, so maybe an easier way to do that is to go to 3 meters right here, and then come over by 0.2 meters. So 3.2, I'm still getting that wrong, because I've got 3.3. Maybe I got it wrong on my sheet. I should have, I've got it wrong on my sheet. I should have come over to 3.2, not 3.3 meters. So my numbers are going to be very slightly off, probably not enough to see a difference. What I'll do is I'll grab a calculator and correct it as I go. Let's make sure that makes sense. 0.6 divided by 3 would be 0.2, so yeah, 3.2 would be the correct location. I've got 3.3 on my sheet, but that's wrong. That's why I like to think through it, because I do make mistakes, and as I've said before, this kind of problem really lends itself to Excel. You should absolutely use Excel for any of these kinds of problems because of things like this. You can make changes very easily, and then those changes propagate through the spreadsheet. It makes it easy to correct errors. Anyway, segment 1 has a height of 0.2 meters for its centroid, or not segment, but area 1. Area 2 would be at 0.4 meters plus half, well not half, but a third of the height, so that's plus a meter. So that should be at 1.4 meters. I'm going to verify as I go to make sure that I'm thinking right. Of course, you can tell already that I've made mistakes on my sheet, but that's okay. 0.4 plus half of 3, well that would be 1.9 meters. This would be 1.5 plus 0.4. And then for body 4 or area 4, I'd go up, let's see, 2 meters plus 0.4, so 2.4 meters total height. Okay, so that should give me x tilde, y tilde. The area in square meters, I will have to just, well, we'll see if it makes sense. See if what I've got makes sense. 3.6 times 0.4, I got 1.44. If we think about it, 0.4, if we take 10%, that'd be 0.1, so it'd be 3.6, or 0.36, which we'd have to multiply by 4. Yeah, so 144, 4 times 36, 144 makes sense. So then multiplying, let's see, for area 2, we get 3 times 1.8 divided by 2, so in other words 3 times 0.9, which is going to be close to 3. I got 2.7, so that makes sense. For area 3, 0.6 times 3, yeah, it's about 1.5 plus what, 0.3, so 1.8, and that's what I got, so that's good. I'm trying to verify my numbers, at least see if they're reasonable in my head. So then for area 4, I would expect to get half of that, 0.9, because it's a triangle, very much like the rectangle. Despite my drawing, the rectangle is half the size of the triangle. So summing all of the areas, you get 6.84, and of course those are square meters, sum of the area. And the next thing to add to the table is the product, or the moment of the areas about the y-axis. So we need x moment arms times area. So all we have to do then is multiply these columns out. 1.8 times 1.44. When you do that, you get 2.592 for body 1. For body 2, 1.8 times 2.7. I got 4.86. Similarly, 4.86 for body 3. And then 2.97 for body 4. Now, we got to be careful because remember I made a mistake here. So 2.97 would be the wrong number. I'll get my calculator and correct the number. Let's see. So I need what? X bar 3.2 times 0.9. Actually, I can do that in my head. All I've got to do is take 10% away from 3.2. Right? So 10%. Yeah, I'll make life easy. 0.9, besides I'll probably make a mistake. It's early in the morning. 2.88. Okay? Before I got 2.97, which was wrong. It was a little high because, of course, I had 3.3 instead of 3.2 here. Finally, y tilde a is the last column. So there we're just multiplying y tilde, 0.2 times 1.44, for example. And you get 0.288 for body 2, 3.78 for body 3, 3.42 for body 4, 2.16. That one should be okay because I didn't have an error in y tilde, at least I think I don't. Summing all of these, because of course one of them is the sum of the, not sum of moments, sum of the x tilde a's, sum of the y tilde a's. These sums will be necessary to locate the centroid of the composite body, or the composite area, I should say. 15.282, 9.648 are those sums. And so x bar, the location of the centroid, sum of the x tilde a's over the sum of the areas. Well, the x tilde a sum is 15.282. I neglected to write it but of course we have meters squared times meters, that's meters cubed, divided by the sum of the areas, 6.84 square meters. And so that gives us just meters for x bar. That comes out to about 2.234 meters. So there's the location. Let's see, so 3.6. Yeah, it's weighted to the right of the center. It's to the right of 1.8, so that makes sense. Everything's kind of leaning that way, if you will, or there's more area distributed on that side. Y bar, sum of the y tilde a's over the sum of the areas. And for that, 9.648 over 6.84. Same units, it'll just be meters, because it's cubic meters over square meters. And I got 1.411 meters. Now, I just realized my sums will be wrong. This sum will be okay, this one's okay, this one will be wrong because of my mistake earlier. So let's fix all of that. The sum I got before, oh, what's the difference? 2.97 less 2.88. That's 0.09. So I should have 0.09 less than what I had before. So this is what I actually had before. If you sum these, you won't get this number. 0.282. Yeah, so I should have had 15.192. That's what I should have had here. And then that is divided by 6. Well, let's make sure this calculator is working like I expect. 15.192 divided by 6.84. So I should have gotten 2.21 meters. But there's the location of the centroid. Now, why would this matter? There we go. Well, the overall centroid shape provides a moment that resists. Remember, there's dirt all behind here, so it provides a moment. It's sort of leaning back, if you will. More force is required in order to bring that center, which is over here somewhere, to bring it well over and get the wall to tip. And of course, that's not going to happen most likely unless we have too much force from the dirt or whatever this wall is holding back. Maybe it's some type of dam or something. So the location of the center of gravity then is where we've noted X bar, Y bar here.